Hi everyone, so this PowerPoint is going to be on global change, especially global climate change for AP Environmental Science. Some of these learning objectives we've already talked about, such as the greenhouse effect and increasing greenhouse gases. We talked about these throughout the school year, introducing them way back in August or September, but we're going to hit them again here and at least review them at their basic level so that we can understand what's going on with global climate change, which is our next learning objective, which again we've been talking about throughout the school year. And we're also going to talk about ocean warming, which we barely talked about with coral reefs, and we'll talk about it again. And then ocean acidification, which we really hit during the carbon cycle. And here's the vocab. If you want to pause this and write it down, you can feel free to, but you don't necessarily have to. And like I said, this is mostly going to focus on climate change. And when we're thinking about climate change, think about the fact that we only have one Earth and that this one Earth is our one home. And if we change the parameters of that system, it is going to affect our well-being because we ultimately depend on the natural systems to survive. And I want to start this off with this quote from the former governor of Washington State saying that we are the first generation to feel the impact of climate change and the last generation that could do something about it. And that is absolutely true, as we will see as we move forward throughout this PowerPoint. Before we get into this, I want to talk about or just remind you guys about generational amnesia or shifting baseline syndrome. Shifting baseline syndrome basically says that what we consider as normal has changed over time in each generation's lived experience, and even within generations, what has become normal is not necessarily what normal was 10, 20, 50, 100 years ago. So the second bullet point with plastics, before the 1980s, there really weren't plastic drink bottles. All those plastic bottles were either glass or metals, and today plastic bottles are ubiquitous. So that has become normal. That last bullet point, talking about the Pleistocene extinction event that Alfred Russel Wallace was discussing. Alfred Russel Wallace was the co-discoverer of evolution by means of natural selection, along with Charles Darwin. And he basically said that we live in a zoologically impoverished world from which the hugest and fiercest and strangest forms have recently disappeared. Talking about the Pleistocene extinction where saber-toothed cats, cave lions, mammoths all disappeared. What was normal to people 10 or 12 or 15,000 years ago is not what is normal today. What was normal in the 1980s is not normal today. What was normal in the year 2000 is not what is normal today. I'm going to skip this slide. I have it in here in case we were doing it in class where we would discuss this. If you want to pause it now, you can answer this question, but I'm going to skip it. And those ways that the planet is changing are listed here. This is not an exhaustive list, but global climate change, including all of those subheadings of global warming, melting ice, melting permafrost, rising sea levels, changes in wind patterns, changes in weather patterns, changes in extreme weather, and ocean warming. We'll talk about ocean acidification, ozone depletion, but that will be on another PowerPoint. Plastic pollution, other solid waste pollution, agricultural pollution, a lot of these things we've talked about before, especially with the pollutants. We're going to mostly focus here on the global change part of it. And then on the next PowerPoint in this short unit, we'll talk about biodiversity and invasive species, remind you what we talked about back in November. All right, so we're going to start with the basics with the greenhouse effect. Now, you guys don't have to write down this slide. I'll never test you on history. You don't need to know history for this class. But people talk about the greenhouse effect as if it was something that was discovered in the late 1900s. That is absolutely not true. The greenhouse effect was known in Charles Darwin's day, back in the 1800s. So in 1824, Joseph Fourier was the first one to propose a greenhouse effect, but he didn't have a mechanism. Basically, what he did was interested in other planets and calculate the temperature of other planets and calculate the temperature of what Earth should be given its proximity to the sun and how much solar energy we get. And his calculations said that it should be about 30 degrees Celsius colder than it actually is. Well, what's keeping the Earth warmer than 30 degrees Celsius colder than it otherwise would be, where the entire planet would be frozen over? Well, he proposed that it was the atmosphere, and he proposed the greenhouse effect. He didn't have a mechanism for it. He didn't know how it worked, but he proposed it. In the mid 1800s, 1856, 1861, in the Americas and in, I believe, Scotland with John Tyndall, Eunice Foote and John Tyndall, independently, or maybe he copied her, the jury's still out, we don't really know, reported that carbon dioxide traps heat and other gases can trap heat like methane and water vapor were discovered at the time and later. So we knew what the greenhouse gases were. Carbon dioxide was a greenhouse gas and it traps heat in the atmosphere. Um, I'm going to So for Svante Arrhenius, he created the first climate models. He proposed that if there was a doubling of carbon dioxide in concentration in the atmosphere, that based off of his calculations, the global temperature would increase between 5 and 6 degrees Celsius. And this was crazy accurate. Before supercomputers, he did all these calculations by hand, and all of the research since has more or less corroborated his findings, except that he thought it would happen way slower than it actually is. We're somewhat approaching a doubling of carbon dioxide. This was before the automobile, widespread adoption of oil, definitely before natural gas. He thought it would take about 3,000 years. We've done it in about 120 years, 130 years since he proposed it. And then in the 1970s, Exxon, before it became ExxonMobil, before it merged with Mobil Oil, so Exxon Oil conducted really pioneering research, like state-of-the-art research on the climate systems, and corroborated Arrhenius's findings. They knew that carbon dioxide was increasing due to their products, the combustion of oil, combustion of fossil fuels, and they essentially just kind of hid that research. But they've been planning for it this entire time. So, for example, they have, and oil companies all around the world have, let's say in the Arctic, they have drilling rigs that are built really deep into permafrost so that when the permafrost melts, the rig stays stable. They have offshore rigs that they've built high enough to um, accommodate for rising sea levels. So they know that it's happening as well. And then they spent billions of dollars in disinformation campaigns to misinform the public since the 1980s, which is why we have the ridiculous debate in the United States of, is global warming a thing? Is global warming not a thing? The companies that are primarily responsible, the fossil fuel companies that are primarily responsible for global climate change, are the ones that are peddling the misinformation and deceiving the public. But they knew exactly what they were doing. So ads like this from 1962, where Humble Oil is bragging about how much energy they produce every year, every day, to melt. Every day they produce enough energy to melt 7 million tons of glacier. So they are aware. So I will try to keep this brief, but because we've talked about this several times, but the greenhouse effect is caused by several different gases in the atmosphere: carbon dioxide, methane, nitrous oxide, some of the fluorinated compounds like hydrofluorocarbons. Water vapor is a greenhouse gas. Those all absorb infrared radiation. So essentially what is going on is that there is shortwave radiation or visible light from the sun that is going through the Earth's atmosphere. These gases do not absorb visible light. Okay, you can't see carbon dioxide, for example. That visible light is going to strike the materials on Earth's surface, and it's going to warm up those materials. So think rock, asphalt, concrete, steel, glass. Those materials are going to get warm underneath of the visible light from the sun, and then they're going to re-radiate out infrared radiation, so heat waves, long wave radiation. They're going to radiate out, and that radiation will eventually go back out into space, where there's going to be heat escaping into space. That thermal radiation or that long wave radiation will escape into space, but some of it will be absorbed by these molecules of greenhouse gases. Those molecules of greenhouse gases will re-radiate out that solar radiation in all directions, back towards the Earth's surface, higher up into the atmosphere, and every side, every direction in between. As they re-radiate out that heat, they send that heat, some of it, back to the Earth's surface, where it gets warmer in the lower atmosphere and therefore warmer on the surface of the Earth. The more greenhouse gases we have, the more heat that they can trap, and the less heat is going to escape into space. The more heat gets trapped in the atmosphere and re-radiated out in all directions, but back down towards Earth, which is the important part for us. It will eventually escape into the atmosphere, but the global accounting, the balance of energy, is going to cause it to increase the temperature of the surface of the Earth. Okay, so think about it like a blanket. The more gases that you have, the thicker the blanket is, the more blankets that you have, keeping your body warm on a cold night in bed. Okay, the less gases that you have, the thinner the blanket. If you just have a sheet, it's not going to keep you as warm underneath of that blanket. So these are the greenhouse gases that are trapping that energy, trapping that long wave or infrared radiation. And like I said, carbon dioxide, methane, water vapor, nitrous oxide, and some of our fluorinated and chlorinated compounds. Carbon dioxide is primarily coming from fossil fuels, from any type of combustion, whether that is the combustion of fossil fuels, whether that is coming from the combustion of biomass, whatever. As well as cellular respiration, both aerobic and anaerobic pathways will generate carbon dioxide. Methane, this is natural gas. So when we're talking about natural gas leaking or methane degassing off of oil, that is releasing methane directly into the atmosphere. Methane has a global warming potential over a 100-year period, somewhere in the range of 30 times as much as carbon dioxide. So if you look at all of these and kind of average them together, it's around 30 times. Over 20 years, it's about 70 times stronger than carbon dioxide because it has a relatively short half-life or a relatively short lifespan in the atmosphere. Methane is also coming from anaerobic cellular respiration. So think enteric fermentation, the methogenic bacteria in the rumen of cattle, sheep, other ruminants. They're releasing methane. The methane that is being released from anaerobic bacteria in waterlogged soils, such as in rice paddies, swamps, marshes, etc. Water vapor. This one isn't super important for our class. It has a relatively short resident time in the atmosphere. It cycles really quickly. It rains out of the atmosphere relatively quickly. It doesn't stay in the atmosphere for thousands of years like carbon dioxide will. This will rain out. However, there is a lot of nuances with water vapor. Increased water vapor, increased humidity will cause an increase in temperature, but that will also create an increase in cloud cover. And clouds shade the surface of the Earth and reflect sunlight back into space. So there's a lot of nuance that we're not going to get into with water vapor. So that's the one that you don't really need to worry about. Nitrous oxide, is coming from agriculture use. This is degassing off of nitrogen-based fertilizers and off of animal manure. So animal manure is just releasing nitrous oxide right into the atmosphere. Fertilizer use is releasing it into the atmosphere. And it is a greenhouse gas that is somewhere in the range of 270 times stronger than carbon dioxide is over a 100-year period. And then our fluorinated compounds, there's a bunch of them. Just know HFCs and CFCs can both be greenhouse gases. And they can range from lifespan in the atmosphere from tens to thousands of years, like tens of years to thousands of years. And they can be anywhere from hundreds to thousands of times stronger than carbon dioxide as a global changing gas. We've seen this slide also, so you may have this in your notes already from the first semester, but the rate of warming. The really worrying thing about the global warming that we have right now is the rate. It is happening very, very, very quickly over the course of a couple hundred years. People that argue that there has always been global climate change, they are absolutely correct in the sense that there has always been global climate change. The Earth's temperature has risen and fallen significantly throughout the entire history, the geologic history of Earth, and we'll see that on some of the next slides. But those processes tend to take quite a bit of time, from hundreds of thousands to tens of millions of years for temperatures to increase and temperatures to decrease. That allows for ranges of plants and animals to shift. That allows for organisms to adapt. Think about the range of plants shifting. If you have a forest that is moving further north, following the glaciers as they retreat, as the planet warms, and then that same forest moving further south as the glaciers advance, as the planet cools, that's going to take time. Trees take a really long time to reproduce, tens to even 100 years to set their first mast of seeds. And those seeds aren't going to go very far most of the time. So a generation of trees has to be seeded, grow, and then drop seeds a little bit further south, whereas the northern ones, if we're talking about the glaciers advancing, the northern part of that population is going to die, but the seeds that are dropped just slightly south or moved further south by animals or the wind will grow. Then they have to have a generation time to set even more seeds. So it's going to take a really long time for a forest to move in front of the glaciers. That takes thousands to millions of years. Again, we're causing this rapid warming in the course of a couple hundred years. So that's the really worrying threat. We're not giving plants and animals enough time to adapt, and we're not giving plants and animals enough time to shift their ranges. And the big thing with shifting ranges is now we have all this human infrastructure in the way, all of the cities, roads, buildings, mines, whatever. And that in part is one of the reasons that we talk about global climate change as a implicator in the loss of biodiversity and the potential sixth mass extinction that we're talking about, or that we've been talking about throughout the school year. All right. And like I said, the Earth has had very warm periods. The Earth has had very cold periods. The last glacial maximum, for example, the furthest south that the ice retreated, 15,000 years ago or so, uh, was only 4 to 6 degrees colder Celsius, colder than it is today. That's global average temperature, only 4 to 6 degrees Celsius colder than today. Okay. The Paleocene-Eocene thermal maximum, the hottest period in the past 60 million years or 65 million years, was only 5 to 8 degrees Celsius warmer than today. This was the hottest period in the in the age of mammals. So if we think about crocodilians, like alligators and crocodiles living in the Arctic Circle, subtropical trees living in the Arctic Circle, that's only 5 to 8 degrees Celsius warmer than today. If we're talking about human-induced, anthropogenic induced climate change leading to a rise in temperatures of 5 degrees Celsius, that is very, very significant. Okay. This range that we're talking about is only about 12 degrees Celsius. So all these variations in global climate are around 12 degrees Celsius, maybe 15 degrees Celsius. Okay. The Cretaceous was only 4 degrees Celsius warmer than today, global average temperature. And again, crocodiles and dinosaurs living above the Arctic Circle. So a very, very different world from just a few degrees Celsius. And again, when people project that there is going to be a 5 degree Celsius increase in global temperature from pre-industrial levels by 2100 or by 2200, that's only a couple hundred years, a few hundred years, not thousands of years. And these rapid changes in temperature are often linked to mass extinction events. So this is just showing a map of the Eocene. Now the green colors are not vegetation, that's elevation, but it's showing that the Arctic and Antarctic are ice-free. And again, you had crocodilians living at the poles. All right, in this diagram, we see that the range of the hottest to the coldest points in Earth history is only about 18 degrees Celsius. So when I said 12 on the other slide, 12 to 18, 12 to 15, different models, different researchers will put different values on it, but the point is the same. It's only a few degrees Celsius difference. 5 degrees Celsius for increased global temperature over the course of a couple hundred years is definitely significant. So how do we read this graph? This is showing the temperature of the Earth through different periods. The time on the x-axis is in a logarithmic scale. In this first section from 0 to 20, we're looking at thousands of years. So this is the past 20,000 years. During the past 20,000 years, we had the last glacial maximum about 15, 17,000 years ago, something around that range, 18,000 years ago. And then this section right here where the climate has been more or less stable. If you follow this red line, climate's been more or less stable. That's the Holocene. That marks from 10,000 years ago the dawn of agriculture, and our agricultural systems have been in a more or less stable climate over the past 10,000 years. Okay, and then the second section, we're going from 20 to 1000, so that's still thousands of years, and we see the up and downs of the ice ages. So the interglacials where the temperature is warmer, the glacials when the temperature is colder. And you notice that during the Eemian interglacial, it was even warmer than it is today. So it's not like these temperatures that we're talking about are unprecedented, but they, the rate of warming is again what we're worried about. And then we go into millions of years. So from this 1000 back to this section, oh, sorry, that's hundreds of thousands of years, my bad, throughout the Pliocene, and then millions of years from here down to around 65 million years where the dinosaurs went extinct. We're talking about millions of years, and you notice this really, really warm part. That's the Paleocene, Eocene thermal maximum, and then hundreds of millions of years after that section. Okay, and the point of this, the planet has been warmer, the planet has been colder in the past than it is today, but it's the rate of warming that we're worried about. This warming, like we'll see in another slide, is closely tied to carbon dioxide concentrations. Increased carbon dioxide will lead to increased global temperatures because it's a greenhouse gas. Decreased carbon dioxide will lead to decreased global temperatures because, again, it's a greenhouse gas. And then what we're showing here is what they call the hockey stick curve, and more or less stable carbon dioxide concentrations throughout the past 2,000 years up to the middle or the beginning quarter of the 1800s, Industrial Revolution, where we start burning massive amounts of coal, followed by oil and natural gas, increasing global carbon dioxide concentrations from the combustion of fossil fuels. We're taking those fossil fuels that have been a carbon sink, where they've sequestered carbon in the geology of the Earth for tens to hundreds of millions of years, and we are burning them and releasing that carbon dioxide that has not been in the atmospheric cycle during that entire time. Those tens to hundreds of millions of years, putting it into the atmosphere, and that is triggering this warming. And one interesting little fact that you don't really need to know for a test or quiz, but is interesting, if you burn fossil fuels, that is going to generate heat, right? But the carbon dioxide that you release into the atmosphere is going to trap 100,000 times more heat than was released in producing it over the course of its lifespan in the atmosphere, because it's going to last in the atmosphere for thousands of years. So for every little bit of fossil fuels that we burn, we're having, over the course of 1,000 years or thousands of years when this carbon dioxide is in the atmosphere, hundreds of thousands of times as much heat as was released when it was combusted. We've talked about Keeling curves, so this shouldn't be new either. This is seasonal variation in atmospheric carbon dioxide levels. If we focus on the graph on the right, northern hemisphere has more vegetation than the southern hemisphere. There's more land mass in the northern hemisphere. So during the northern hemisphere summer, all of that vegetation is drawing carbon dioxide down. That vegetation is photosynthesizing during the northern hemisphere summer and locking that carbon dioxide into plant tissues, into organic molecules. Then during the northern hemisphere winter, carbon dioxide increases because of all the cellular respiration, whether that is animal, fungal, or plant respiration occurring in the northern hemisphere and all over the world during the northern hemisphere winter. The southern hemisphere doesn't have enough vegetation to photosynthesize during the northern hemisphere winter, southern hemisphere summer, to counteract the massive amount of cellular respiration that's occurring in the northern hemisphere. All right, and then summer draws it down, and then winter releases carbon dioxide. But there is an overall increase in carbon dioxide that is over top of this due to the combustion of fossil fuels. So you see this summer winter variation, but the overall trend upward is due to the combustion of fossil fuels. And if we just look at carbon dioxide over the past few decades, I'm going to start with a graph in 1960 or 1958 when this data started. So Keeling started collecting this data in 1958 when the carbon dioxide level was around 315, 317 parts per million in the atmosphere. As we go through the 2000s, essentially what I did was like for my class of 2025, you guys are seniors right now. I'm assuming that most of, if not all of you guys were born in 2007 when the carbon dioxide concentration in the atmosphere was 384 parts per million. And then you can track it through your lifespan up to 424 parts per million in 2024. Okay, this number you guys should know. You should know that the concentration of carbon dioxide in the atmosphere is around 420, 424 parts per million, somewhere in that range. If you say 424, that's great. If you say 420, that's great on a test. And these Keeling curves are publicly available. So on this one, I have spring of 2020 to spring of 2022, which is just when I made this slide. But you can go onto their website and pull this data. It is publicly available. And we can again see the entire Keeling curve from 1958 to, in this case, 2022. And then bring it out further. So before 1958, it is ice core data. After 1958, it's the direct observations of atmospheric gas concentrations from Mauna Loa. We'll talk about ice cores in a second. But ice cores are also direct measurements of atmospheric gases. Again, drawing it out throughout the past 2,000 years, you notice that during the past 2,000 years, carbon dioxide was very stable in the Earth's atmosphere until the Industrial Revolution. When we talk about pre-industrial levels, the benchmark that we typically use is 1750 because there was a little bit of coal that was burned in the late 1700s. So we go with 1750 most of the time for pre-industrial levels. You guys notice that pre-industrial levels were hovering right around 375, 380 parts per million. Sorry, 275, 280 parts per million. I'm sorry about that. You guys know how I am with numbers. So pre-industrial levels, 275, 280 parts per million. Again, today we're around 424 parts per million. And again, we stretch this out throughout the entire history of human agriculture, so the past 10,000 years, give or take, for agriculture. And you notice that there is more or less stable carbon dioxide concentrations, and that it does rise ever so slightly. That is mostly due to land use change. That's mostly due to, starting in this region of 265-ish parts per million up to this 270, 280 parts per million. That's mostly due to land use change that humans have done over the past 10,000 years as we've cleared forests, as we've cleared grasslands, and we've released that carbon dioxide into the atmosphere through the combustion of that vegetation or the decomposition of that vegetation. Okay, so land use change does play into this, but after the Industrial Revolution or during and after the Industrial Revolution, combustion of fossil fuels is the primary driver of the hockey stick, hockey stick curve. Again, note that this is throughout our agricultural history. This is why we've been able to grow the same crops in the same areas over the past 10,000 years, is because it's been a more or less stable carbon dioxide concentration, which makes a more or less stable climate. And then what do you think is going to happen to our more or less stable climate as we increase carbon dioxide, right? How is that going to affect agriculture? Well, we can use the ice ages as a proxy for that, possibly in one sense, in the sense that the climate has changed a lot in the past million years. So if we look at from 800,000 years ago, we again see interglacials where it is warmer and glacials when it is colder, when the ice retreats, when the ice advances, right? The ice advances during the colder periods, the ice retreats during the warmer periods. And we can see that climate has changed quite a lot in the past the past 800,000 years. Okay, this isn't necessarily showing climate, but this is showing direct measurements of carbon dioxide using ice core data and after 1950, just atmospheric measurements at Mauna Loa. So what is this ice core data? Ice cores are where you bore into ice sheets. So the Greenland ice sheet, the Antarctic ice sheet, this ice that hasn't melted for the past, 800,000 years, million years, 2 million years, since the Pleistocene began. You bore down into into these ice sheets, and you extract these cores of ice. And in these cores, it's basically like tree rings, where every year there's a new layer of snow that falls. That snow is going to slowly compress down into ice, and as it does that, it's going to trap little bubbles of air that you see in the top right picture. It's going to trap those little bubbles of air as that snow compresses down into ice. That air is the atmospheric air of the year that that snow fell. So you can take these ice cores back to the lab and you can, um, keep them frozen throughout their entire journey, put them into a vacuum flask where you've sucked out all of the modern atmospheric air, let them melt in that vacuum, and let them release their air, the air that was trapped in this ice 100,000 years ago, 200,000 years ago, 800,000 years ago. And then you can analyze that air. So this is like a time capsule of the atmospheric conditions um, for the past 800,000 million years. Okay. Currently, we're increasing carbon dioxide concentrations at a unprecedented rate. Every year, give or take, there's about 50 billion tons or 50 gigatons of carbon dioxide equivalents going into the atmosphere. Those are additive for the most part. Carbon dioxide is going to last in the atmosphere for thousands of years. The fluorinated compounds the hydrofluorocarbons are going to last for thousands of years for the most part. Methane is relatively short-lived. But in general, think about these as additive. We add 50 billion tons this year, we had 50 billion tons last year, we had 50 billion tons the year before that, and those are additive in the atmosphere. So just those 3 years alone would be 150 billion tons. So these greenhouse gases are accumulating in the atmosphere. I do keep this relatively simple by saying that we add 50 billion tons every single year, but as we have seen throughout the course, that is actually growing. So we're adding around 50 billion tons of carbon dioxide equivalents every year recently, but they are increasing. So a few years ago, it was 45 billion tons. You know, it is increasing. And this graph is a very similar graph to the one that you saw on the last slide, where it's just showing where this carbon dioxide is coming from. And On the last slide, it was a pie chart. On this slide, it's just a line graph, but this one is showing the rate of growth for some of these. Electricity and heat is the fastest growing sector for carbon dioxide. Transportation around the world, manufacturing and construction are also growing. Stuff like land use change and forestry is actually either staying the same or even decreasing. So we can see where this carbon dioxide is coming from, or the carbon dioxide equivalents, I should say. So where this carbon dioxide increasing, we are seeing warming. Temperatures are often compared to pre-industrial levels. So usually we say 1750 is the pre-industrial level, or it could be the average of many decades. So I'm trying to write 1750 with my mouse, which doesn't really work super great, but 1750 is usually what we use as the pre-industrial level. But we could also compare it to averages of many decades. So for example, we can take the entire 100 years between 1850 and 1950, the general start of the Industrial Revolution, to the mid 20th century, and average all of that, and then compare modern temperatures today in the 21st century to those temperatures. So there's a lot of ways to measure it. 2024, the average global temperatures were 1.28 degrees Celsius above pre-industrial levels, and in the past 10 years, we have seen the 10 hottest years on record. So 2014 was the hottest year on record, and then each year after that has also seen the hottest years on record. Not necessarily saying that it was that 20, well, I mean, you guys can see it on the graph, but these are the hottest years on record. Not necessarily saying that 2021 was hotter than 2020. It's that these are the 10 hottest years. So just clarification on that. And we see that since the middle of the 20th century, that global temperatures on average have been increasing. And the reason for that is primarily because the oceans were absorbing a lot of that excess heat. There was a lot of heat that was being absorbed by the oceans, and the oceans were buffering the global system during the early part of the 1900s, as well as the fact that the greenhouse gases are both cumulative and increasing in amount, increasing in rate of emissions throughout the 20th century. So we're and the 21st century. So we're releasing more carbon dioxide in the past 20 years than they released back in the 1940s to 1960s. Okay, so carbon dioxide is increasing both in emission of, in terms of it being faster rate of emissions, it being cumulative in the atmosphere, it's additive, it all adds on to itself, and then the fact that the oceans were masking much of that warming throughout the 1900s. But the point of that was to show that global annual temperatures are increasing. You guys have seen this animation. I really like this one, where it shows every single year since the 1800s and average temperature. So each one of those red lines that flashes by really quickly is corresponded to the date at the top. And we see that the red lines for average temperature are increasing. This one is comparing average temperature from 1951 to 1980 as our baseline reference. So 0 degrees is the average of all the years between 1980 and 1951, or 1951 to 1980. Average all those together, global average temperature, all the temperatures are all around the world throughout every single day, every single season. Average all those together, that's 0 degrees Celsius on this graph. And then the difference between those, the earlier years before the 1950s were cooler. The years afterwards were warmer, and that warmth is increasing and increasing at an increasing rate. It's accelerating. So I'll let it finish one more time. And that acceleration of warming is tied to the Great Acceleration. It's one of these factors in the Great Acceleration, which is the continuous, rapid, and often exponential growth of a variety of human activities and impacts on the natural world. So these are all human activities, or vaguely human activities. Population is not an activity, but tied to activities. And you see that the human population has grown exponentially. GDP has grown exponentially. Energy use has grown exponentially. Water use, telecommunications, international tourism, paper production, all of these things have tolls on the natural world. And we've talked about all of this before. You guys have even seen this slide before. And then these are the Earth system trends. So carbon dioxide, nitrous oxide, methane, three greenhouse gases increasing at exponential rates, although you see that methane is tapering off there at the top in this diagram. I've seen others where it is growing exponentially, just really does, it's not logarithmic like it is in this diagram, just really depends on the study, the authors, what data they use, all of that stuff. It's really complex. Surface temperature, what we're talking about mostly now, increasing throughout the latter half of the 20th century at a more or less exponential rate. All of these other things growing at either a exponential rate or for some stuff like domesticated land starting to taper off because we've already used most of the easily accessible domestic land that's really good, or wild lands, we've turned them to domestic for growing our crops. Okay, but again, great acceleration. This is more the Earth system trends, the natural trends that we're seeing in the world, and what we're focusing on here is surface temperature. So right now, the climate models are projecting that mean global temperature will increase between 1.1 and 5.4 degrees Celsius by 2100, depending on what model we use. Now, we've already hit 1.5. So in 2024, we hit a few days or like a week or so where it went global average temperature above 1.5 degrees Celsius above pre-industrial level. But the average for 2024 was less than 1.5 degrees Celsius. Most of these models, in fact, all of these models include some overshoot. So if we take 2.0 degrees Celsius as our what the Paris Climate Accord wants us to get to or to stay at, most models today, because this graph is becoming a little bit dated, will have us dip above that and then go below. And that section is overshoot, just like we talked about overshoot with population growth. 1.5 degrees Celsius, basically all of these would include some level of overshoot with that. At least today. So that's not reflected on this graph because this graph is maybe 5-10 years old. And today we've already basically just about breached 1.5 degrees Celsius. So what do these different lines represent? Well, the black line is very likely to exceed 4 degrees Celsius. This is one model, computer model that uses tons of different climate variables, tons of different human activity variables. And this is showing basically business as usual. If we take no climate mitigations whatsoever, if we don't reduce emissions, we're going to see 5 degrees Celsius by 2100. Effective current pledges. So these pledges are what countries have said that they will do, not really held to any legal standard, but said that they will do for the Paris Climate Accord. And that's still going to bring us to between 3 and 4 degrees worth of warming by 2100. And most countries aren't even doing what they pledge to do. They just pledge something and then don't really follow through with those pledges. So we're not really following that. We're more so following the black line right now. Keeping it below 2 degrees Celsius, keeping it below 1.5, keeping it even touching 1.5 and then getting back down to 1. Those are going to include some massive changes at a geopolitical level and at an economic level, which we are just not seeing. The entire system has refused to change, and we haven't seen that kind of those greenhouse reduction revolutions that we were talking about even just 10 years ago or 15 years ago. So right now, what we're looking at is more so this black line, and that's not the ideal situation. The ideal situation is to stay down here. So if you guys are at home, what I'd like you to do is pause this now to watch this short video. It's about 1 minute, 2 minutes, something like that. And if we're in class, we'll watch it in class. We already mentioned this quote, so I'm going to not talk about that again. All right, before we get into the details of global climate change, I've talked a little bit about global climate change before, but we mostly just talked about global warming before. I want to talk about some semantics with those two terms. Now, when I was a kid and when I was a student, we basically just talked about global warming. Global warming at the time encompassed all of those things. We basically said that the planet was warming, and that's going to cause shifting weather patterns, shifting climate patterns. Today, we use the term global climate change because for a few reasons. Because global climate change is a bigger umbrella term that encompasses everything else. It includes warming. It includes shifting weather patterns. It includes more extreme weather events. All of those other things that we'll talk about in the subsequent slides. And because global warming, although is occurring, there are a few places around the world, notably the North Atlantic and the South Atlantic, where we're seeing some cooling trends, and those are anomalies that we'll talk about and why that is important. So most authors are talking about global climate change today, or they use that term because that encompasses warming and everything else, and because not everywhere is warming equally. All right, so before we get into climate change, a couple pieces of legislation or a couple treaties. The first one you do need to know for the AP exam, so definitely know the Kyoto Protocol for the AP test. This is one of the 11 pieces of legislation that we need to know for the class. This is a 1997 treaty. You don't need to know any dates for the class, but you should know it at least in historical context, 1997, so the mid-90s. The attempt was to reduce the emissions of six greenhouse gases and specifically like hydrofluorocarbons and perfluorinated carbons or perfluorocarbons, my bad, perfluorocarbons are kind of groups of gases. We're not really going to talk about perfluorocarbons, just think hydrofluorocarbons when you think about them, but they're different. They don't contain hydrogen. And we're not going to really talk about sulfur hexafluoride, even though they are both on this list and they're both strong greenhouse gases. Um, Carbon dioxide, methane, nitrous oxide, you guys know. Hydrofluorocarbons, you guys know. Now, the goal was to reduce greenhouse gas emissions by 5% compared to 1990 levels from 2008 to 2012. So between the range of 2008 to 2012, we were going to attempt to reduce our emissions of these greenhouse gases to below 5% or by 5% of 1990 levels. So the goal was we were seeing increasing carbon dioxide and other gases, greenhouse gases in the atmosphere. The goal was to reduce those gases over time so that their concentrations plateaued. Remember that they stay in the atmosphere. So if you reduce them down to no further emissions, they're just going to remain steady. They're going to plateau in the atmosphere. Okay. And then a further reduction between 2013 and 2020 by 18% compared to 1990 levels. Now, obviously, we have failed with that. Instead of the concentrations of these greenhouse gases decreasing over time, we have actually just that was pretty bad, but we have actually seen them just continue this exponential growth and increase over time. So we have obviously failed with the Kyoto Protocol. We did not meet either of those targets. Some of the criticisms, why did that happen? Well, there was no penalty from withdrawing. There was no penalty for not achieving the goals. So if there's a piece of legislation with no penalty and is basically voluntary, then what's the point of the piece of legislation? If you're not going to, like if the law says don't steal, but you don't get in trouble if you steal something, then is there any incentive not to steal? No. And the same thing applies here. The U.S. didn't ratify this treaty, so we were not a member of this treaty. We decided not to ratify it, so we weren't held to anything. So yeah, and then China and India were developing, so they were classified as developing nations, and they did not have to reduce their emissions because this really did apply to developed nations first, and then less strict regulations or less strict limits for developing nations. Okay. And then there's the Paris Agreement or the Paris Climate Accord. This is one that you do not need to know for the AP exam. This is a UN treaty that was signed in 2015 and then initiated in 2016. The long-term goal was to keep um, global average temperatures below 2.0 degrees Celsius above pre-industrial levels. Again, that pre-industrial level is 1750, with below 1.5 Celsius being ideal. Now, why they included this 1.5 degrees Celsius is because 1.5 degrees Celsius is when we think that some of the there's going to be significant sea level rise that will lead to the inundation of some island nations. So they were really pushing for that 1.5 degrees Celsius. The method was to reduce emissions of greenhouse gases and to create new carbon sinks and to maintain existing carbon sinks. So if you could plant a mangrove forest where mangrove forests have been deforested, if you can replant that forest, then that would be one way to remove carbon dioxide from the atmosphere and sequester it in both biomass and the soil in those mangrove forests. The criticisms, there is no global mechanism or standards, so there's no like one way to do things. There's no like set list of rules or standards. Each country basically develops their own specific emission targets. So if one country says we're going to reduce our emissions by 15%, another country could say, well, we want to reduce our emissions by 1%. So there's not really much of a specific emission target. There's no dates associated with it. So we can say we want to reduce our emissions by 10% over by 2030, or we want to reduce our emissions by 10% by 2050. There's no like rules or set methods of achieving those goals. And there's no penalty for not hitting those targets. There's no penalty for not really complying with the treaty at all. You can sign it and then not do anything, and there's no penalty. And then with the United States, we did sign this treaty. We were a member nation until we withdrew in 2017, but technically we couldn't withdraw until 4 years after signing it. Signing it. So we couldn't withdraw until 2019 or November of 2020 is what I have written here. Maybe it was after it was initiated. And then we were formally rejoined in 2021. And then, sorry, I had the highlighter rather than the pen. And then we announced our withdrawal again in January of 2025 due to American politics. So Paris Climate Accord is on track of failing, just the way that Kyoto was on track of failing as well. And this temperature that we see in this graph is expected to continue to rise. Now let's talk about what we're going to be talking about throughout the rest of this PowerPoint, which is basically like the nitty-gritty of climate change. So we're going to talk about how the Arctic is warming. We're going to talk about rising sea levels, warming oceans, distribution of storms, distribution of droughts, heat waves, all of these different things. You don't really have to write any of this down because we'll talk about all of them on their specific slides. All right, and we're going to start with changing atmospheric circulation patterns. So do you guys remember Hadley cells? It's been forever since we talked about them, way back in first semester, first quarter. Hadley cells are this first band of atmospheric circulation cells, north-south circulation cells in the tricellular model of atmospheric circulation. So as a reminder, warm air rises at the equator. Warm, humid air rises at the equator, like where the Congo rainforest here is, and then it precipitates out as it moves towards the higher latitudes. So you get precipitation going north from the equator, but then by the time that it descends around 30 degrees north and 30 degrees south, it descends as relatively cooler, dry air. That is still going to be relatively hot because it's air that came from the equator and is descending, but it's going to be dry air that falls or that descends in around 30 degrees north and south, which creates our desert bands around the world. So the reason that we have the Arabian and Saharan deserts there is because of this this model of atmospheric circulation. The reason that we have the Namibian desert in the south, same reason. Okay, so warm, moist air rises at the equator, and then it's going to rain. So this entire section we see savanna and tropical dry forest, until it descends as this air descends as relatively cool, dry air at 30 degrees north and south. Now these bands shift with global temperatures. So as we increase the temperature, these bands are expected to move higher into the northern latitudes. So rather than around 30 degrees, it might be more like 35 degrees, 37 degrees, 40 degrees north and south. So that's going to shift our desert regions further north. So the Mediterranean region is expected to become drier. Southern Europe is expected to become drier. And we see this in the fossil record and in the geologic record. So the both fossils and rocks. All right, so this is going to increase the size and the distribution of these mid-latitude deserts where they're going to move into the higher latitudes. So South Africa will become more arid and Colorado may become more arid. All right, and the next atmospheric circulation pattern that we'll discuss is the jet stream. The jet stream you may have heard of on the news. The jet stream is what we often look at with weather patterns in the United States. It is a consistent band of westerly winds, winds that originate in the west, moving east. So they're moving in this east direction. So it's called a westerly because it originates in the west. So moving from the west to the east, which is why our storms in Colorado typically develop over the Pacific, and then they move to, let's say, Washington State, and then through Idaho, and then down to Colorado. Okay. So the distribution or the changes in the jet stream are due to differences in temperature. Historically, back in the day, the jet stream was very, very stable, like we see on this diagram, where we have this stable jet stream that looks like this halo around the Earth. Okay, that stable jet stream is due to significant temperature differences between warm air south of the jet stream and cold air north of the jet stream in the Arctic region. The more different those two areas of temperature are, the more stable the jet stream is. If there is a more drastic difference between the warm, more southerly air and the colder, more northerly air, then it's going to be a stable jet stream. But as the Arctic is warming and it's not quite as cold in the Arctic, if we have warm air both south of the jet stream and north of the jet stream, that leads to this wobble in the jet stream. And that wobble is going to bring down cold Arctic air. Now I had the diagram on this diagram, I put the W for warm. That's showing that it's warmer than it was. Rather than it being like, let's say, negative 20 degrees Celsius, maybe it's just 10 degrees Celsius. So that temperature difference is not as severe. If the warm air in the continental United States is, let's say, on average, I don't know, 15 degrees Celsius, and it was negative 20 up above in the Arctic, versus we still have 15 degrees Celsius and let's just say negative 10 degrees Celsius, then that can lead to this wobble in the jet stream to where we get this cold, still cold, but warmer than it was, air descending into the continental United States. So these polar vortexes, these polar bombs that they'll talk about on the news, or Arctic bombs, this unpredictable weather in the continental United States, where you have this band of cold air descending into the southern states due to instability in the jet stream. So big takeaway, if there is a greater difference in temperature north and south of the jet stream, then the jet stream is stable. If there is less of a difference between the cold air in the north and the warmer air in the south, then that jet stream is going to be more unstable and is going to quote unquote wobble, and it's going to cause cold air to descend down into the United States, into the central United States, among other things. And a really good example of that is the 2021 Texas deep freeze, where we have the jet stream wobble, bringing, I'm going to change colors and make it more of the highlighter style, where we have this jet stream that is, sorry, I can't figure out how to do the high. Okay, there we go. This jet stream that is bringing this cold air further south into the United States. In this case, into the central United States, Oklahoma and Texas. Okay. During this event, There were very, very, very cold temperatures, unusually cold, like -9 degrees, -17 degrees, -12 degrees in New Mexico, Texas, Oklahoma. That is very, very, very unusual. And that was so cold that it froze the wind turbines. Wind turbines in northern states have all kinds of technologies on them that like antifreeze that will allow them to not freeze during the winter. But Texas didn't invest in that because they're a southern state and they didn't think that they needed to because historically they haven't experienced these cold temperatures. So the wind turbines were not winterized. They didn't have the antifreeze like stuff in them to prevent them from freezing. So they froze, they locked up, and they didn't produce any electricity. Simultaneously, the natural gas lines also froze because they were also not winterized. So 4.5 million homes and businesses went without power. There were food, water, and heat shortages, and about 250 people died. And this is definitely exacerbated by the private ownership of the Texas grid. We don't need to get in the weeds with that, but Texas is their grid has some history behind it. All right. So although freezes do occur in Texas, we never see, or at least very, very rarely see these -17 degrees Fahrenheit temperatures. All right. So this is just one example of that jet stream instability. And one more thing about that jet stream instability is that people will use that as an argument against climate change. Like, I just had the coldest day ever in Texas. Planet can't be warming because this was the coldest week that I've ever experienced, and I've lived here for 80 years. That's actually not an argument against climate change. That's actually an argument for climate change, right? As we have seen. So some other effects, more extreme weather events. Essentially, what is going on is that with warmer air, we have more energy in the atmosphere. Temperature is just a measure of the kinetic energy of molecules. So the more kinetic energy there is, the more energy of movement there is, the higher the temperature is. And that's just energy. That's just a measure of energy. So the warmer it is, the more energy there is in the atmosphere. Also, the warmer it is, the more water vapor is going to be in the atmosphere, the more humidity will be in the atmosphere if there is a source of that humidity. Obviously, if you're in a bone dry desert and the temperature increases, you aren't going to increase the humidity. But if you're near the coast, if you're in an area that is humid before, as you increase the temperature, you're going to increase the humidity. For each 1 degree Celsius increase of air temperature, you are going to increase the water vapor potentially as much as 7 degrees or 7%, my bad, 7%. Okay, so hotter air holds more water vapor. If you have higher temperatures, if you have more heat, and you have more water vapor in the atmosphere, you're going to have stronger storms. There's no two ways around it. If you have more energy, you're going to have stronger storms. If you have more water vapor that can condense down and form clouds and water droplets, you're going to have stronger storms as well. All right, so what we're seeing is more extreme weather events, and the weather events that we're seeing are also increasing in severity. That includes hurricanes, typhoons, and cyclones. That includes thunderstorms, tornadoes, and flooding rains. But the frequency of storms may also decrease, and we're seeing that as well. Fewer rains, but more severe when it rains. I've heard accounts of farmers that have been farming in the Midwest, like Illinois, Idaho, or sorry, Illinois, Iowa, in Ohio, Indiana, those states where they would say in the spring, back when they were kids, 50, 70 years ago, it would just be like every spring you would get days of drizzling rain. But today you're not getting those drizzle rains as much. You're getting these thunderstorms that come through once or twice a week, dump lots of rain, possibly even so much that erodes away some of the soil that you just planted. The seeds that you just planted erode away with the soil, and it's more difficult to farm. So the frequency of those storms is decreasing. You're not getting daily drizzles of rain, but you're getting the same amount of rain or even more potentially in heavy rainfall events once or twice a week. And since we're talking about surface waterways and since we're talking about precipitation, let's talk about snowpack. So in temperate regions, we have snowpack. Snowpack is, especially in the mountainous areas, snowpack is the snow that accumulates over the course of the winter and packs down into ice, or at least packs down into really condensed snow. Um, As the planet warms and as the temperate regions warm, what we're seeing is that the first snowfall is occurring later in the autumn. All right, so we have later snows in the autumn and the winter, and we also have earlier spring melting. The last snow of the season is typically earlier in the spring or the late winter, and we're seeing the melting starting earlier in the spring or winter. And those two combined are decreasing our snowpack. Okay, so in this graph, we have 23% decrease in April snowpack in the western United States from 1955 to 2022. That is exacerbating the drought in the western United States. If we have less snowpack, that is our that's the source of the water for the rivers in the arid western United States, especially the desert Southwest. If we have less snowpack in the Colorado mountains, that's going to mean less water available for people further downstream in Utah, California, or Arizona, or Mexico that are trying to do agriculture. Okay, so if we have decreased precipitation or at least decreased snowfall, maybe the same amount of precipitation, but it's rain rather than snow, we don't build up that snowpack. And then as the snows all melt during the beginning of the spring and the summer, we get a rush of water into our waterways, and we don't get that sustained melting throughout the summer months that we used to have with the snowpack in the western United States. And these changing weather and climate patterns do have effects on soils. So as places become more arid with the expanding Hadley cells leading to the expansion of the mid-latitude deserts, we're expected to see less vegetation holding that soil in place and desertification due to wind and water erosion. There will still be some rainfall, and that rainfall may fall in more extreme bursts, so long droughts interrupted by heavy rainfall events, which is going to facilitate those soils drying out and then eroding away during those flooding rains. So that will lead to the expansion of deserts, so desertification. And then some places that are seeing more severe storms can experience more severe flooding, which will also cause more severe erosion. Some of those places are going to see periods of prolonged drought, same as the more desert areas, and then heavy rainfall events where it's going to erode away even more because that soil dries out and is more easily eroded. But even areas like what you see in the bottom right, which looks like a tropical rainforest, where it is always wet most of the time, heavy flooding rain can still cause severe erosion. And finally, these shifting climatic events can lead to something known as phenological mismatch. Now, phenological mismatch, you don't need to know the term. Do not memorize this term, but just know the basic process. If you want to break down the term, I'll do it for you. Phenology is basically the study of the life timing events of plants and animals. So if you think about like in the spring when the buds of the trees open, the flowers open. That's a phenological timing event. And then in the fall, when those leaves start to turn color and then they drop off the trees, that's phenology, the study of life, the timing of life cycle events. All right. It could be bird migration, flowering, insects hatching from their eggs, all of these different things. Um, these timing events, these life cycle timing events are influenced by daylight hours, which we are not changing, temperature, which we are definitely changing, and precipitation, which we are also changing. Okay. Now what's going on? If we have birds that are migrating and they know historically for generations and generations and generations when they migrate, they have a food source waiting for them. Say that the fruits all all ripen at the same time and the birds migrate through and they can eat the fruits on their way south during the autumn or during the spring. They know that all the insects are going to hatch at a specific time. There's going to be lots of caterpillars on the new leaves of the trees that have just opened up in the spring with these new young caterpillars on them. They move north, they eat the caterpillars, and then continue moving further north in their migratory routes. That can all be changed by this. If the um, let's just say that the birds are migrating based off of daylight hours and the insects are hatching based off of temperature, as temperature increases, the insects might hatch early, and then they might not be there, or they might be in a later life stage, like they may be in cocoons if they're caterpillars by the time that the birds get there. So these life cycle events may be mismatched. And the examples that we see over here on the right, if the birds historically laid their eggs based off of sunlight hours um, earlier, and we have the the eggs hatching. Maybe this is based off of temperature with the sun. I'm not sure. The eggs hatch, and then those young chicks are ready for the adults to get the caterpillars and bring it to the chicks to eat the caterpillars. If they start nesting earlier based off of temperature, but the caterpillars are at the same time they're later based off of daylight hours or something, then those chicks may go hungry because they're not there at the same time as the caterpillars. Okay, I know that was a little bit convoluted, but it's basically that um, daylight hours remain consistent, temperature changes. So if they're doing something based off of temperature and another organism is doing something based off of daylight hours, those may not line up anymore like they did in the past. And the temperature is changing so rapidly that they may not be able to adapt and coincide. Okay. The last example that I have down here, if a hummingbird migrates north based off of daylight hours, but the plants are blooming based off of temperature, the plants may be blooming earlier and the hummingbirds may not be there to pollinate the plants. So the plants suffer because they're not reproducing, and the hummingbird is suffering because they are not getting their food source. All right, let's move into the oceans. So, do you guys remember the thermohaline currents or the ocean conveyor belt or the Atlantic meridional overturning circulation pattern or AMOC? This is essentially that warm water from the equatorial regions of the Atlantic. Warm surface water floats and it's going to move up to the North Atlantic where it is going to cool. As it cools, it becomes more dense, so it's going to sink. And as it cools, it freezes, and that freezing kicks out the salt that's dissolved in that water. So you basically get more or less fresh water ice that forms during the North Atlantic winter. And that cold water that's left behind is more salty, so it's going to sink because it is both colder and more salty, and both of those make it more dense. So this cold water, let me shift over to the blue, that cold water sinks and slowly moves all the way down throughout this entire thing to either the Southern Ocean where it will rise, the Indian Ocean where it will rise, or the North Pacific where it will rise. This entire current can take thousands of years for one water molecule to make this entire trip. But this is basically distributing thermal energy around the world. This is allowing for the really hot tropics to cool down a little bit as we have cold water coming up and as we have that warm water moving north and flowing or sinking down. All right, so with these AMOC currents, these can be disrupted by influxes of warm or cold water. If we add a lot of warm water, it can disrupt these currents, or as we're doing right now, adding a lot of cold water that is fresh from the melting Greenland ice sheet and heavy North Atlantic rainfall that can slow down these currents, that can stop them even. So we have seen a documented 15% slow of the AMOC since 1950. And disrupting these currents can lead to a cascade of events. Those could include further warming. That warming could be more severe at the tropical regions because that warm water is not moving up north and redistributing that thermal energy. Those tropical seas may become hotter. It could also usher in cooler parts of in the North Atlantic, and Northern Europe could be colder because that warm water in the tropics is staying in the tropics and not moving further north to cool to warm off northern to warm up Northern Europe. So, like for example, right now Ireland is relatively warm, even though it's at the same latitude as like frigid places in Canada, because it has this warm current that is keeping it relatively warm. We could see a collapse of the West Antarctic ice sheet due to this. We think that that's what happened during the Eemian period or the last interglacial, the warmest of the last interglacials. Disruption of food chains as nutrients are not brought up from the depth. So we have these disruptions of upwellings, which you guys should remember from the biomes. And we may not have as nutrient-rich feeding grounds for many of the fish that we rely on, both humans and wildlife, and increased storm severity, especially along your coasts. So let's just look at one possible outcome of this. Now for this, you don't really have to write anything down. You don't have to take notes on it. I just want to show one historical precedent or one historical model of what could happen and of what people think might have happened in the past. There's still a little bit of unknowns here, and we don't for sure know that the draining of Lake Agassiz led to the Younger Dryas. All right, so the Younger Dryas. The Younger Dryas was one of many of the glacial phases during the past 2.5 million years. The Younger Dryas was we were basically coming out of a glacial period. It was warming, and then we have the Younger Dryas, and this was the last of the ice ages, right? It was the most recent one, and it was a rapid cooling event, rapid in geologic terms, not as rapid as the warming that we're seeing today due to human activity. But it was a rapid increase of the ice sheets, a rapid expansion of the ice sheets. And this was also where many of the iconic megafauna, like the woolly mammoths, the woolly rhinoceros, the mastodons, the giant ground sloths, the saber-toothed cats, this is also the period where they all went extinct. Now, were they driven extinct by humans, by climate change, or a combination of both? This is an active debate, but the strongest evidence points to human overhunting and trophic cascades that resulted from that and from competition. Now, one hypothesis to explain the Younger Dryas, this rapid cooling event, was a disruption um, of the Atlantic Meridional Overturn Current, the AMOC, and that was due to a rapid increase of fresh water into the North Atlantic. There was this giant lake called Lake Agassiz. Lake Agassiz was larger than any of or all of the Great Lakes, all the modern Great Lakes combined. So this shaded in area is Lake Agassiz, larger than all the Great Lakes combined today. And it was held back by glacial dams. Glacial dam is basically that you have a glacier that is damming the river. So maybe a glacier between two mountains and like a canyon, and the river that is draining this lake is dammed by that, and it's keeping this lake intact. Now, if you have the collapse of a glacial dam, you're going to have a rapid flooding event. So that entire lake could drain, or at least a large section of the lake could drain, if you have the break of a glacial dam. And they think that a glacial dam broke either along the Hudson River route, through the northern Canada, or along the St. Lawrence Channel, that dumped a lot of fresh water all at once into the North Atlantic, disrupted the AMOC, stopped the AMOC, and plunged the northern hemisphere back into an ice age when it was in an interglacial period, or at least coming out. So as the North America was warming, the Laurentide ice sheet, which is in this uh, um, hashtag, no, this dashed line around here, as this glacier melted and the subsequent, or the ice sheet melted and the glaciers around it melted, that the glacial dam broke and that it added lots of fresh water into the North Atlantic and stopped, or at least very much slowed down, the AMOC and led to a um, sorry, I'm trying to fix the pin situation. I got the highlighter. And it led to the glacial period. Another issue that we're seeing in the oceans is that the oceans are getting warmer. As the atmosphere gets warmer, the oceans get warmer. But water does have a very high specific heat. It takes a lot of energy to raise the temperature of water just a little bit. So you may recall from biology class or chemistry class that specific heat is the amount of energy that it takes to raise anything by 1 degree Celsius. It takes a lot of a lot of energy to raise the temperature of water. And in fact, the oceans have absorbed about 93% of all atmospheric heat from the excessive greenhouse gases. This has masked the warming effect or buffered the warming effect that we otherwise would see in the atmosphere. If it wasn't for that, the atmospheric temperatures would actually be 36 degrees Celsius warmer compared to pre-industrial levels. So most of that heat is getting absorbed by the ocean. Most of that energy is getting absorbed by the oceans. That's why we haven't seen an immediate increase in global temperatures, global atmospheric temperatures, after greenhouse gases started to get released in the Industrial Revolution, because the oceans were taking up much of that excess heat, and that's why there's this lag time. So the mean ocean temperatures have risen by about a third of a degree Celsius since the 1960s. Um, that doesn't sound like a lot, but as we've talked about in this class, the warming is unequal and different organisms have their own ecological tolerances, and that warming can be enough to change metabolic rates and reproductive rates, to change different life timing cues, and to cause coral bleaching. Okay. The second issue with warmer oceans is that they're going to contribute to sea level rise. Because warmer water expands relative to cooler water, it's going to expand and it doesn't have anywhere to go. It can't go up, it can't go to the sides, it can only go up, and that's going to cause sea levels, and it is causing sea levels to increase. If there's a greater difference between warm surface water and cold deep water, the thermocline that we talked about first semester, then that's going to slow the mixing. It's going to slow those thermohaline currents. It's going to slow downwellings and upwellings. And again, marine heat waves cause coral bleaching events. All right, so a recap on coral bleaching. We talked about this and you guys saw this slide during first semester. So quick recap, photosynthetic corals are symbiotic organisms. The coral polyp itself is an animal related to sea anemones, and the algae that's inside of them is a zooxanthellae algae, a term that you don't need to know, and that algae is photosynthesizing. So the coral polyp is filter feeding, and the algae is photosynthesizing. When the coral becomes stressed, it will kick out its algae. So the stressed coral will cause the algae to leave those coral polyps. They're actually inside inside those cells, and they'll eject those algae, and that will cause the corals to lose their color, because the algae are what are giving them their color with their photosynthetic pigments, and that coral will appear white, and that is what we call bleached coral. So it's like bone white. If the coral is left bleached for any period of time, it's going to die. Okay, so they become stressed and they kick out their symbiotic algae and they die. So what causes them to become stressed? Well, some types of runoff and pollution. Not a huge one for this class, but yes, exposure to sunlight. But the big one is the change in temperature. Okay, so the big one for us is going to be change in temperature. The marine heat waves that we see cause corals to bleach. All right, and we are seeing, like I said, that the oceans are increasing in temperature by about a third of a degree Celsius. So somewhere in this region is the average for the data that I got on the other slide. But you see that it is even increasing further than that in most recent years. This graph does top off very recently at 2025. On the left, we have global. And on the right, we have the temperate regions between, or at least the northern temperate region between 30 degrees north and 60 degrees north. And that region is warming faster than the rest of the world's oceans. So the northern temperate oceans are warming faster than the rest of the world, and that there is going to be variation based off of El Nino and La Nina cycles. So there's going to be warm years and cool years, especially in the Pacific Basin. But all that aside, we do see that global average ocean temperatures are increasing, and that there are increasing marine heat waves. And these heat waves, you don't need to know any specific heat waves, but these heat waves are affecting coral populations. Remember again that marine heat waves and warm sea surface temperatures are going to cause coral bleaching events, not ocean acidification, heat waves, and some types of pollution. And we see that some of these heat waves are confined to areas or in areas where we see lots and lots of corals, especially the South Pacific around Australia and Oceania and Southeast Asia, as well as in the Caribbean. All right, and the next thing that we're going to look at is sea level. So we've talked about two of the three variables in these or the two or the three measurements that they're looking at in these three graphs. We've looked at carbon dioxide concentrations, we've looked at temperature. What we're going to look at now is sea level. And you can see that they are all three correlated with one another throughout, in this case, the past 400,000 years. Again, we talked about how temperature and CO2 are correlated. They also are correlated with sea level. Why is that? Well, because as the planet cools in ice ages, so in times when the planet is much colder, we have lots and lots of ice, or lots and lots of ice that is locking up lots and lots and lots of water. That water is ultimately going to be coming from the oceans. It's going to evaporate from the oceans and then form clouds, move over land, precipitate out, and if that is precipitating as snow in an ice field or an ice sheet or on a glacier, then it's going to compact down into ice and it's not going to melt for the foreseeable future. Then when we have warmer periods, such as right here, that's going to cause lots and lots and lots of melting. All rivers are going to lead to the sea, or at least most rivers are going to lead to the sea. Some lead to large inland lakes, but most rivers lead to the sea, and all of that ice that is melting from glaciers, ice sheets, ice fields are going to enter the oceans and cause sea levels to rise. And we see that there is quite a difference between some of the glacial maximums around 400 feet lower sea level than today, and then today. So in order to talk about this, I am going to cover the types of ice that we have on the planet. Um, Not something that's huge for the AP test or something that you really need to know for the course, but it's something that these are terms I'm going to use and terms I want you to be familiar with. So an ice sheet, this is a large expanse of perennial ice, meaning ice that does not melt year after year after year, that covers over 50,000 square kilometers. So that is a very, very, very large expanse of ice. Today on the planet, we have two ice sheets. We have the ice sheet on Greenland and the ice sheet on Antarctica. So basically, the entire interior of Antarctica is an ice sheet. There are ice fields. These are smaller, but they're still large expanses of perennial ice. So down here, I have a picture of some mountains in Alaska where we have ice fields. This is perennial ice, and all this ice that is between these mountains doesn't melt even in the summertime. This is when I took the picture during the summer, and it doesn't melt, and it's perennial ice. And they are often terminated by glaciers, or they often have glaciers that are at their margins. Okay, what is a glacier? A glacier is perennial ice that moves under its own weight. So it's basically like a river of ice. If we look at this glacier, it is flowing towards the sea, downhill, from this ice field that is the interior, all around those mountains. Okay, so a glacier is moving ice, whereas an ice field and an ice sheet are more or less static. Ice shelves, these are large platforms of ice that are floating on the ocean and attached to mainland glaciers or mainland ice sheets, or sorry, yeah, mainland ice sheets or mainland glaciers. So this is the ice shelf, that section right there. It's floating on the ocean below it, and it's attached to the glacier on the continent or on the island or whatever on the land. Okay. An iceberg is a floating mass of ice. So you guys are probably all familiar with icebergs, but they are floating masses of ice. Many of them are breaking off of ice sheets, ice shelves, or glaciers, and they're floating and being carried out to sea. And then sea ice. This is frozen seawater that floats on the open ocean. So when we talk about the seasonal sea ice in the North Sea or the Arctic Ocean, we're talking about ice that freezes during the winter and then melts during the summer. Some of it is going to stick around year after year after year. Some of it's going to stick around for maybe a couple decades. But increasingly today, we're seeing that it forms during the winter and then melts during the summer. So it's just seawater that is frozen, as opposed to all the other ones which are land-based. All right, so with these types of ice, what would you expect if global temperatures rise? Well, you would expect for this ice to start melting. If it's warmer out, the ice is going to melt, right? If it gets above freezing for any extended period of time, then the ice is going to start to melt. Where does this meltwater go? Well, some of it will seep down into groundwater. Most of it will flow out to the ocean via rivers, and very little of it is going to flow into a large inland sea or a large inland lake via rivers as well. Most of it, the overwhelming majority, is going to go into the ocean. If we have a large influx of water into the ocean, it should be no surprise that sea level is going to rise. So many glaciers around the world are melting. Many of those are shrinking. Some of those have completely melted. And this one in Iceland was the first one in Iceland to completely disappear. And in 2019, they put up this funeral plaque for it saying that OK is the first Icelandic glacier to lose its status as a glacier. In the next 200 years, all our glaciers are expected to follow the same path, meaning that all the glaciers on Iceland are expected to melt in 200 years. This monument is to acknowledge that we know what is happening and what needs to be done. Only you, speaking to future generations, will know if we did it. And it's dated as August 2019 with CO2 levels at 415 parts per million in the atmosphere. And this is not confined to Iceland. Anybody that has lived in or traveled to Alaska has probably become familiar with glaciers. And even if they don't want to admit it, or even if they don't want to admit it, anybody that lives in Alaska can see the effects of these melting glaciers because all the glaciers are, or at least the vast majority, I'm not aware of any of that aren't retreating, but I'm going to say like the overwhelming majority of glaciers in Alaska are retreating, just to cover my bases in case there is like one or two that aren't. But basically all of them are retreating. What we see here is the Juneau Glacier and the Juneau ice field actually, and then all of the glaciers around it and how they are retreating. The warmer colors, like down here near Juneau, are showing that it is retreating at an accelerate or really, really fast. Um, if you talk with people in Juneau, like when I visited Juneau, the old timers in Juneau will talk about how much closer to the city the glacier was, how much more bigger it was, and how much more impressive it was than today. And one thing that is really cool with some of this glacial loss and some of this ice loss is the before and after photos. You can find historic photos and then take a modern photo at basically the same spot with the same vantage point using the same mountains as reference and see how much ice has melted. So if we look at July and the summer of 1909, we see all of this ice in this section of Kenai Fjords National Park versus August 2024 where it is all open water. And then the same thing with these images of Bear Glacier at Kenai Fjords National Park in Alaska. This is in southern Alaska, or at least south central Alaska, September 2002 to August 2007, so summer months in both of those. And we see how much ice has been lost just in 5 years from this glacier. The same thing is occurring further south in Montana at Glacier National Park. It's actually expected that by the end of the century, that Glacier National Park is not going to have any glaciers at all. That it's going to be called Glacier National Park, but there's not going to be any glaciers because they're all melting. Same thing with like it's just like the state of California with their flag. Like there's a brown bear on it, but they're extirpated from California. They've all been killed a long time ago and extirpated from the state of California. So here's another series of photos from Glacier National Park showing multiple years, multiple photos. And you can see how much the ice has retreated. Same thing is happening in Colorado. This is Andrews Glacier up in Colorado, Rocky Mountains. And I kind of went nuts with this, but here is Greenland, 1930. 2022. I'm not sure exactly where in Greenland this is, but Greenland is losing a lot of ice, probably more than anywhere else. It's actually, I was reading an article just a week or two ago about how Greenland now has 35 more small islands than they used to because the ice is melting along the coast and it's revealing these new islands. They were previously covered in ice, looked like it was all connected from the mainland. You can walk along the ice from mainland Greenland to the edge of the sea and didn't even know that you were standing on a rocky island. But once the ice all melts, now these islands are being revealed. That's not what we're seeing here, but that is happening. Greenland is actually gaining more coastline than anywhere else on the planet as the ice is retreating. So here's another couple photos from Greenland. Again, ice retreating. Like I said, I did go nuts with all of these pictures. I think the before and after pictures are really good tell of how much ice has been lost. These pictures are up in the islands of Svalbard, so a small archipelago that Norway owns up in the Arctic Circle, and you can see the glacier loss and both the mountains and humans as a reference. And then another series of pictures, again with the landscape and people as a reference. So 1939 up to 2002, and then you can see how much ice was lost, especially down in this section between 2002 and the present, but also over here and off in the distance. You can see how much ice was lost. And then another angle of the same glacier up in Svalbard. And again, you can see how much was lost over the course of 70 years or, whatever, and then the course of 20 years. And even just in the course of 12 years in the European Alps, I'm not 100% sure where exactly this photo was taken. It was just cited as the European Alps. So I'm not sure what country, but same thing. Doesn't matter where, you can see that the ice has been lost. And it's happening in the Himalayas, the Andes, every other mountain range around the world. We're seeing glacial loss. So if you're watching this at home, check out this video. It's really interesting. It's the largest glacier calving ever filmed. We'll watch it in class. And the amount of ice that is lost just in this one event is absolutely astounding. It's mind-boggling to think about how much ice was lost just in this one glacial calving. So check it out if you're at home. We'll watch it in class if we're in class. All right, and with all of this melting ice, again, all rivers lead to the ocean, so that water is going into the oceans. And although the oceans are vast, we are seeing sea level rise. And sea levels are rising because of two things. One is because of the melting ice that is allowing water to flow into the oceans and therefore rise their levels. And then the expanding ocean waters, because they are warmer, they are expanding, and that is causing sea levels to rise as well. There's been a documented rise just using tide gauges throughout the 20th century of about 8 inches or 20 centimeters. So since from 1900 to 2000, we saw an 8-inch increase in sea level. That rate is about 1/8 of an inch a year, but is accelerating. At the early parts of the 1900s, it was slower. At the latter parts of the 1900s, it was faster. So it is accelerating. And some communities have absolutely felt the effect of this. The Isle de Jean Charles in Louisiana has lost about 98% of its land since 1955. This photo was taken in 2016, and even more recent photos show that it is even more inundated. So there are communities that are being affected by sea level rise today, and some of these communities have people that have been displaced. At the Isle de Jean Charles in Louisiana, I don't want to say for certain, but a significant portion of their population has been relocated. They have moved out, basically become climate refugees in the United States because of rising sea levels. So politicians will argue that sea level rise is not occurring. We have a documented rise just using tide gauges and historical records of 8 inches over the course of 100 years. And that doesn't even include what we've seen in the 21st century so far. If all this ice that we're talking about melts, we could see an increase of 70 meters, which is 197 feet. Now, that's not going to happen for thousands of years. It's going to take thousands of years for all of the Antarctic ice sheet to melt. But just to give you an idea, the Greenland ice sheet alone contains about 7 meters of sea level rise, the West Antarctic ice sheet about 5 meters, the East Antarctic ice sheet 52 meters. This is where the majority of the ice in the world is, and that's where most of the fresh water in the world is. And then if we have all the mountain glaciers that melt, that's about 8 meters of sea level rise. All right. So again, we are seeing a documented sea level rise. The y-axis here is in millimeters. So we were talking inches. I showed centimeters, but this is in millimeters. So just be aware of that. When it shows 200, don't freak out. That's not 200 feet. That's 200 milliliters. Millimeters. Can't speak. Um, Over the past couple decades, we've actually had satellite data in there as well. I neglected to mention that, but all the rest of this, the black line on here is tidal gauges, tide gauges, and the orange line is satellite data. So we can measure sea level by satellite, and it's much more accurate. And then we see where the melting is occurring in Antarctica, and you see that the deeper the red color, the more melting that we are seeing, especially in the west portion of Antarctica versus the east. The west Antarctic ice sheet is is uh, melting at a faster rate than the east Antarctic ice sheet. So I want to share this quote with you guys. It's about sea level rise. It's from the president of the Republic of Palau. He was speaking at the World Leaders Summit at COP26, which is the conference of the parties for essentially the UN's climate agency, the IUCN, their conference of parties in 2021. He said, the scorching sun is giving us intolerable heat. The warming sea is invading us. The strong winds are blowing us every which way. Our resources are disappearing before our eyes. Our future is being robbed from us. Frankly speaking, there is no dignity to a slow and painful death. You might as well bomb our islands instead of making us suffer, only to witness our slow and fateful demise. He's talking both about climate change and rising sea levels inundating this small coastal, or sorry, the small island nation. And when we talk about sea level rise inundating nations or affecting communities, we can't not talk about the Republic of Maldives. This is the lowest lying country in the world. The Maldives only have a population of about 500,000 people. They are expected to be the first country lost to rising sea levels because they have the lowest lying topography. Their highest point is Mount Villigny. I'm sure I'm not pronouncing it correct. It's only 16 feet above sea level, so to call it a mountain is a little bit of an understatement. But it's only 16 feet above sea level. That's the highest point on the entire group of islands. The second highest point is about 8 feet above sea level, and their average elevation is 3 feet above sea level. They are actually constructing an artificial island that is hopefully going to be higher than sea level rise is going to see in the next foreseeable future. But if we get to catastrophic levels of many, many meters of sea level rise, they're not going to be able to build anything that's going to protect from that. And then this is going to have effects in the United States as well. Obviously, the United States has an extensive coastline, and many of our major cities are along the coast. Think Baltimore, New York, Boston, Houston, Miami, all of those coastal cities will be impacted by rising sea levels. Additionally, habitats will be lost. Some species may not be able to colonize new habitats up the continental shelf. So as the sea level goes up, you may have some species colonizing that new inundated land and actually having more or new habitat. But will the sea level rise be too rapid for them to shift their ranges? Corals are really slow moving and really slow growing. Like they don't move. They move by each generation, just like we talked about with trees. Will they be able to colonize new areas fast enough to keep up with the rising rate of sea levels? All right. If you're at home, play around with this map. This link is on Schoology. You can type it in from here. Maybe you can click on it here. I don't know. I think it's in the description of this video also. But play around with this map and you'll see how the coastline of the eastern portion of the United States is going to change with rising sea levels. If we only have, like what I did was on this picture and this screenshot was zero point 0.9 meters. So if we have zero point 0.9 meters of sea level rise, Miami is underwater, right? New Orleans is underwater. Houston is underwater. These major cities on the U.S. coast will face losses with significant sea level rise. Yes, we can construct seawalls. Yes, we can do other things like make levees and pump water and all of that stuff. But really, the power of the ocean is going to overwhelm any human structure. So I'm also going to share with you this quote from Greta Thunberg, and from the Climate book, which is her most recent book. She says, our so-called leaders still think that they can bargain with physics and negotiate with the laws of nature. They speak to flowers and forests in the language of US dollars and short-term economics. They hold up their quarterly income reports to impress the wild animals. They read stock market analyses to the waves of the ocean like fools. So it's really getting to the heart of this business versus environmental issue, how business as usual cannot keep going forward and not expect environmental consequences because the laws of physics, the laws of chemistry, the laws of nature dictate what will happen. And nothing that we can do in the economic realm is going to, at least with business as usual, is going to change any of those outcomes. All right, and speaking of chemistry, let's talk about something completely different. Ocean acidification. So we're still talking about the oceans, but we're not talking about temperature anymore. What we're talking about is elevated carbon dioxide levels still. That carbon dioxide levels being higher in the atmosphere is going to lead to more carbon dioxide dissolving into the oceans. And as carbon dioxide dissolves into the ocean, it's going to react with water. When it reacts with water, it's going to form carbonic acid. And what we're seeing here is the overall equation, the reduced equation. I forget what you guys call it in chemistry, but the overall equation where we're not seeing that carbonic acid being reflected. That carbonic acid is going to dissociate. So carbonic acid is H2CO3. Sorry, I'm writing with my mouse and it's not very good. But H2CO3 is carbonic acid. That is what is made from carbon dioxide reacting with water. That is going to dissociate, and one of those hydrogen ions is going to pop off, and it's going to start to dissolve the calcium carbonate exoskeletons of marine organisms. So calcium carbonate, it's also known as calcite, which is not one of our vocab words. Calcium carbonate is fine. And when it does so, it's going to break down those shells, just like what we saw in class. When we put those shells, the seashells in vinegar and they dissolved over the course of a couple of weeks, that's what's going to happen. It's going to lead to the like those shells to just dissolve. It's going to result in weak, thin, and absent shells, especially on mollusks, corals, foraminifera, and many other photosynthesizing organisms, and anything with calcium carbonate shells. And we are seeing a documented decrease in ocean pH. So remember that the decrease in pH is an increase in acidity. As I've reminded you guys many times this year, think of the pH scale, 1 to 14, and then 7 is neutral. Anything between 1 and 7 is acidic. And again, I'm trying to write with my mouse, which is not pretty. And anything between 7 and 14 is either basic or alkaline. Okay. And if we start with a pH of around 8.3, which is what historically the oceans were, and we reduce that pH closer to 7, so getting towards 8.0, 7.9, then it's becoming more acidic. Okay. All right, and a lot of that chemistry is reflected here in this diagram. So you can check it out. We kind of went over it, but carbon dioxide is going to dissolve into the ocean, react with water to make carbonic acid, which we see here. That carbonic acid is going to dissociate into bicarbonate, which is useless for marine organisms to build their shells. They really need carbonate. They can't use bicarbonate, and it's going to create a hydrogen ion. That hydrogen ion is available to knock the calcium off of calcium carbonate shells and exoskeletons and to create even more bicarbonate, which again is useless. So that's what we're seeing here, that hydrogen ion knocking off the calcium off of the calcium carbonate, which is their exoskeletons or shells or, whatever. Much of the carbon dioxide, between 20 and 30%, that we have emitted since the beginning of the Industrial Revolution has been absorbed by the oceans. That is translated to about a 30% increase in acidity. Again, a 30% reduction in pH. And remember that pH is a logarithmic scale, so going from 8 to 7, that is a 10 times increase in acidity. Going from 7 to 6 is another 10 times increase in acidity. So even if it just goes from 8.3 to 8.0, that is a very significant, about 30% change in acidity. Okay. And like I said, this is having an effect on a wide range of organisms, everything that creates a calcium carbonate exoskeleton or shell, as well as everything that feeds on those organisms. So the exoskeletons of corals are impacted. That stresses corals, and it can lead to reduced growth rates. And even if it becomes significant enough, the erosion or the dissolving of those exoskeletons. The exoskeletons of many different phytoplankton, including foraminifera, diatoms. Diatoms, I think, are actually silicate based. I should probably cross that out. But foraminifera and many of the other phytoplankton that you see down here and down here. Remember that phytoplankton are the microscopic single-celled photosynthetic organisms in the ocean. They're the base of most oceanic food chains. If we lose those, we lose those food chains. The entire food chain collapses. The shells of mollusks, the quote unquote skeletons of many marine species like starfish, all of these are going to be impacted. Not only those organisms, but with increased acidity, we also push other organisms out of their range of tolerance. It can impact fish hatching rates. We can impact the health of young fish and just move many species to the edge of or out of their range of tolerances and lead to extinctions. All right, and the next thing that we're going to talk about are climate tipping points. So these are similar to ecological ceilings, which we won't really discuss in the class. I'm going to use the term tipping point. And let's think about a tipping point in like a conceptual sense first. So we've all seen this in class where we have somebody in class, usually a boy, that is leaning back in his chair. And he leans back in his chair and goes far enough that he almost falls, but he like catches himself and pulls himself forward, or he shifts his body and moves his center of gravity forward, and he goes back to a normal seating position. And then he leans back again, and then the same thing happens, and then he goes back to a normal seating position, and then he leans back even further, and he goes beyond what is called a tipping point to where he is in a free fall. He's not able to recover, and he's just going to go to a different physical state, which is flat on his back on the ground. Right? With this diagram over here on the right, we have two basins, and the high point between those basins is the tipping point. Imagine that the system, whatever that system is, whether it's the Greenland ice sheet, whether it is permafrost melting, whether it is a boy on a chair, if you push this ball up this hill just enough that it's not going to get up to this tipping point, it's going to roll back down the hill and then back into basin A. And then you push it up with a little bit more strength, and then it only gets to about right here, and it's only going to roll back down into basin A. Then you push it up with a little bit more strength, a little bit more strength, and you get it past this tipping point, and it's going to fall down into basin B. It's a irreversible state change. Okay, and this is often going to be caused in climate science by positive feedback loops. Okay, or these are going to cause positive feedback loops, these tipping points. All right, so what are some of these tipping points? You guys don't really need to know all of these tipping points for the class, but you should know them for real life because this is where we're going at current rates of CO2 emissions and at temperature increases. The ones on here that are bold are expected to occur within the next few hundred years. The ones that are not bold can take thousands of years. So like the East Antarctic ice sheet, for example, the collapse of it might occur within or take 10,000 years for it to totally occur. It's going to take a lot of time for it to completely occur. Also, there's a lot of regional tipping points, and all of these tipping points have a temperature associated with them. Most of them adding to the global temperature, but some of them cooling the planet. All right, so Arctic winter sea ice collapse. So the collapse of all of the sea ice in the Arctic Ocean during the winter, having an ice-free Arctic Ocean. Because you free up so much water, and we'll talk about this in the next couple slides, that will absorb thermal energy. That's going to increase the global temperature by about 0.6 degrees Celsius. The entire collapse of the Greenland ice sheet, boreal permafrost collapse. We'll talk about permafrost in a little bit. East Antarctic, West Antarctic ice sheet collapse, the East Antarctic subglacial basins collapse, all of those adding a small amount of warming. Amazon rainforest dieback. So the Amazon rainforest actually produces about half of its own precipitation. About half of the water that goes into the Amazon rainforest as rain originates through transpiration of leaves from the Amazon rainforest itself. The rest of it comes from the Atlantic Ocean. So as that rainforest dies back and as that rainforest gets cut down by human activity, we lose that transpirational water loss, which could reduce the amount of precipitation or rainfall in the Amazon rainforest and then cause a tipping point where there is a point of no return where the rainforest is just going to start dying back because there is not enough precipitation. Um, and then the last two you see are adding, or sorry, subtracting some temperature increase. So have negative temperature increase. The Labrador Imminger Seas convection collapse. So this is one of those oceanic convection currents. And then we talked about the AMOC collapse as well, and how that may lead to cooling in the northern hemisphere. And then this diagram shows some different tipping points. So stuff like coral reef die-offs, some of those more regional or global, but global and regional tipping points. And these ones are identified in this diagram. It's interesting. Check it out, but I'm not going to go over it. I was reading an article a few weeks ago by a new article published in 2025 by Jim Hansen, who is one of the who's like a legend in climate science. And he stated that the most threatening tipping point, the point of no return, will be passed when it becomes impossible to avoid catastrophic loss of the West Antarctic ice sheet with sea level rise of several meters. Large areas of China, the United States, Bangladesh, the Netherlands, island nations, and at least half of the world's largest cities will be substantially submerged, an irreversible result. Rising seas will be accompanied by increasing climate extremes that are already emerging at global temperatures of +1 to +1.5 degrees Celsius above pre-industrial levels. The last time Earth was at +2 degrees Celsius relative to pre-industrial time in the early Pliocene, sea level was 15 to 25 meters higher than today. So the West Antarctic ice sheet is really one of the scariest ones for most climate scientists today, and the associated amount of water that's going to go into the oceans and that was going to melt from ice, go into the ocean and trigger massive sea level rise. And the reason for that is that the West Antarctic ice sheet, so if we're looking at a map of Antarctica, and I know that it's pretty small, Western Antarctica is over here. The West Antarctic ice sheet is in large part supported by bedrock that is under water. Like it's ice sheets that are supported by ice shelves that are supported by bedrock that's underwater, including mountains. And as that water warms, it melts the bottom of the glacier of those ice shelves. So those ice shelves melt from the bottom up. And as they melt, they become weaker, and that could lead to a potential loss of that ice sheet support. So the entire thing could collapse into the ocean. The most scary one of that is the Thwaites Glacier, which is again supported by underwater bedrock, and it is melting at a very rapid pace. So I got a couple videos that you guys should watch at home if you're doing this at home. We'll watch these in class if we're in class. Talk about tipping points and about destabilizing ice shelves such as the West Antarctic ice sheet or those associated with the West Antarctic ice sheet. All right, now, so for the AP test, what you guys need to know are two of these tipping points. So we're going to talk about those two. So when we talk about these, we're going to talk about these in the context of positive feedback loops. So a positive feedback loop is essentially where the end product of a cycle further contributes to the action of that cycle. It's a self-perpetuating cycle. And you guys will see what I mean, but it's a cycle that feeds itself. All right, and these two that we're going to talk about aren't any worse than other tipping points, but they're occurring very rapidly. They're occurring like we can watch them occurring in many cases, and they're the two on the AP learning objectives, which is why we're going to talk about these two. The first one is what I'm going to call the ice albedo positive feedback loop. Now, just to remind you guys, again, all the way back from first semester, albedo. Albedo is the reflectivity of a surface. Like a mirror, think about that as like 100% reflective. It has 100% albedo. All light that strikes a mirror gets reflected off into your eyes so that you can see a reflection. So it's the reflectivity of a surface. Fresh snow, I'm sure that all of you guys have walked out of a dark building, maybe like a movie theater, into the outside world after it has snowed, and that fresh snow is blinding bright because the sun, it just snows, the sun comes out, and you walk out of a dark area and it's like blinding. Fresh snow has about 80% albedo. Old snow, about 59% albedo, ice, 35% albedo. So the point is that ice and snow is very reflective, whereas land surfaces like rock and even oceans are not reflective at all. Oceans and lakes, we might think about them as reflective, but they're not. They absorb 92% of the incoming solar radiation. They only reflect out 8% of it. So why is that important? It's important because of this feedback loop, the ice albedo positive feedback loop. So again, ice has a high albedo, snow has a high albedo, meaning that reflects solar radiation back into space before it becomes absorbed by surfaces and before that visible light turns into infrared radiation. So before it turns into heat waves. Water, rock, and soil have low albedo, meaning that they're going to absorb thermal energy and slowly radiate out long wave radiation back into the atmosphere. And that long wave radiation is what is absorbed by greenhouse gases. So the feedback loop is sea ice, ice sheets, and glaciers are all melting due to warmer temperatures, and that is replacing high albedo surfaces, the ice, with low albedo surfaces. Think about like an area that is iced over and then a small patch of it melts and exposes dark rock beneath it. That dark rock absorbs thermal energy and it's going to warm up the surrounding ice, the ice that's touching it, and it's going to lead to further melting, which is going to expose more rock, which is going to warm up even more, which is going to melt more of the ice that's touching it at its margins, which is going to widen that circle of melted ice, exposed rock, which is going to melt more ice, which is going to expose more rock, which is going to heat up, which is going to melt more ice, et cetera, et cetera, et cetera, et cetera. That happens in the oceans with sea ice as well. Once you have a hole in the sea ice, it can continue that. You guys can actually observe this in real life in a parking lot. If you have a parking lot that hasn't been plowed and you see one small section of asphalt that has poked through the ice, that's maybe like an area where the wind whipped up the snow off of that section of parking lot, that area is going to expand more and more and more and more over the sun under the sunlight as it melts the ice that's at its margins. Okay. So the loss of the Arctic ice, especially, is the primary reason that the Arctic is warming faster than anywhere else on the planet because we have all of those dark surfaces, the soil, the rock, and the water that's absorbing all that that solar radiation in the like the North Polar region, the northern Arctic. All right, but this is happening around mountain glaciers from the equator to the poles. This is happening as well in the Greenland and Antarctic ice sheets also. And we can track that from the same paper that I mentioned, that I took that quote from Jim Hansen earlier, and all the other authors, the contributing authors. We can see that Earth's albedo has decreased over time. So that ice around the world is melting and it is decreasing the overall albedo of the Earth, meaning that there is more exposed rock, ocean water, and soils that are absorbing sunlight and re-radiating out long wave or thermal radiation, infrared radiation, and less of that reflective surface, the snow, the ice, is reflecting sunlight back into space. And again, this is contributing to further warming of the entire planet, but mostly the Arctic because that's where the melting is occurring most rapidly. The second positive feedback loop that we're going to talk about is the Arctic permafrost methane positive feedback loop. Okay, so remember that permafrost is soil that is permanently frozen at depth. That depth could be many, many, many meters, tens of meters, up to 80 meters deep, and it's permanently frozen. Now, if we think about that soil, so imagine that this is like a soil column, the first few centimeters will thaw during the summer. And that's just enough for shallow rooted grasses, mosses, some shrubs like willows to grow. In some areas, it's just enough for some shallow rooted trees to grow. So, like Sitka spruce up in Alaska can grow on permafrost a little bit, but it doesn't really like it. It struggles. Um, and those forests aren't as healthy of trees as forests that are not on permafrost. But the few centimeters will thaw every single summer and then freeze again every single winter. But beneath that, it is permanently frozen soil for many, many, many meters. Okay. Again, permafrost can be vegetated with trees, but more often it's mosses, lichens, grasses, forbs, which are herbs, flowering plants, as well as some shrubs, especially low growing shrubs like willow. As all those plants die, they continually build up organic matter beneath them to form peat. And let's say that only 5 centimeters or 10 centimeters thaws every single summer, and if you add 3 centimeters of organic matter every single summer, then you're going to continually be freezing that organic matter that is being buried deeper. So if you add 3 centimeters of organic matter and it's frozen or it thaws out 10 centimeters up, then like the organic matter that was thawing last year, that's 13 centimeters down, is now frozen. And it's going to be remaining frozen for thousands of years in many cases. So decomposition is going to be really, really slow in this top layer because it's very cold, even in the summer in the Arctic, in the tundra. So decomposition is going to be really slow. It tends to be acidic soils, so that slows decomposition even further. And all of that organic matter ends up getting frozen. And we have lots and lots and lots of organic matter in all these soils that could, if they thaw out, potentially decompose. Okay, I'm talking about that's frozen at depth in the permafrost. All that organic matter, um, if it thaws out, is like a carbon bomb. It has large quantities of carbon dioxide and methane that could be produced from the aerobic and anaerobic cellular respiration of decomposers that end up decomposing that organic matter after it thaws. So again, permafrost contains lots of organic matter. Whenever we think of soils with high organic matter, think lots of carbon and think very dark brown or black soils. And we can see that in this picture in the bottom right. This white is actually ice. Those are ice wedges that are in this permafrost. But the dark color is due to all that carbon. So all of this, all of that is lots and lots and lots of carbon and partially decomposed organic matter or peat. That peat was frozen, but now it's thawing, and as it thaws, it releases carbon dioxide and methane as it decomposes. Carbon dioxide and methane are both greenhouse gases, which are going to lead to further global warming, which is going to further melt more permafrost, which is going to lead to more decomposition of that organic matter that is thawing, which is going to add more carbon dioxide and methane to the atmosphere, which is going to increase global temperatures even further, which is going to accelerate warming of the tundra and the permafrost, which is going to melt the permafrost, which is going to release carbon dioxide and methane from decomposition, et cetera, et cetera, et cetera. Okay. And it's estimated that there is 1,400 gigatons, so 1,400 billion tons of methane trapped in the permafrost. Not only is this methane trapped in the form of organic molecules that can be decomposed and turned into methane, but there is also methane itself, like the gas methane is trapped in these ice in this permafrost and these ice wedges and in the permafrost itself. So it can just directly release methane into the atmosphere when it melts as well. So one really innovative solution for this is something called Pleistocene Park. This was not initially to save permafrost, but it is being proven that it does save permafrost. If you're going to watch one of these, I'd actually recommend this longer one because it gets more into the science of how the permafrost gets saved by rewilding the tundra. So check it out if you're interested. I'm not going to require that you watch this. All right, super short slide. We've talked about this all the way back to first semester, but polar habitats, the polar regions are the most affected by warming global temperatures. They're warming the fastest compared to any other region on the planet. And as we lose that ice, we lose organisms that depend on that ice, or those organisms have to adapt, or they have to migrate, um, and they may not be able to. Polar bears, walrus, seals, they really do depend on the sea ice for habitat. So if we lose that, then those populations could be lost if they don't adapt. So with polar bears, for example, we're seeing that they are moving further south and onto land during the summer months, and they're interacting with grizzly bears, which are moving further north and actually hybridizing with grizzly bears. And we're also seeing that they are seeking other unconventional food sources and trying to change some of their behaviors to survive. Walruses are extremely impacted because they haul themselves out onto the ice to rest. And on this section of film, you see that walruses that are hauled out on islands, and there's too many walruses in too small of an area, can have serious impacts on one another and lead to population declines. All right, kind of cycling back to changes in global temperature. This is shifting ranges of organisms due to increasing temperatures. We've talked about how tropical mosquito-borne illnesses are expected to occur more frequently and to higher latitudes as the mosquitoes that transmit them, so like the mosquitoes that transmit malaria, for example, follow the warmer temperatures from Africa into Southern Europe or from Central America up into the United States as the planet warms. So those ranges um, of those vectors, the mosquitoes in this case, are changing. I'll show you about the US Department of Agriculture. They had to update their vegetative maps in 2012 to reflect the upward shift in plant life, and then they had to do it again in 2023. So even though some agents in government are going to dispute global warming or global climate change, they're going to argue against it with no evidence on their side, just misinformation and disinformation. The US Department of Agriculture, very practical people. They have to serve farmers who themselves are very practical people. They know that it's happening because they've had to update their maps. Lobster fisheries in south of Massachusetts have basically shut down. You used to be able to catch lobsters south of Massachusetts, but today you can't because the lobsters are moving north to follow the colder waters and to flee from the warmer waters as they advance. There's tons of examples. I can spend an entire PowerPoint on just this one slide. But here's the map for the U.S. Department of Agriculture. Kind of move the play bar of this video back and forth so that you can go back and forth between this picture and the next picture and check out specific regions around the country and where those ranges are shifting. This is the 2012 map, and then I'll show the 2023 map on the next slide. So this is the 2023 map of the USDA's gardening zones. If any of you guys' parents garden or anything, you're probably familiar with some of these numbers. Like for Denver, we're in zone 5, but in this map, they're separating things out into zones, not just 1, 2, 3, 4, 5, 6, etc., but also A and B. And you can see a little bit more detail when you add zones A and B into each of those. So go back and forth between the previous slide and this one to check out this shift in those ranges as the warmer temperatures are advancing. And I don't want you guys to think that humans are immune to shifting ranges because we are living organisms, we're animals, and we have our own set of ecological tolerances, and one of those is temperature. And there may be limits to survivability of humans. And that's due to something called the wet bulb temperature. So I'm going to go through this kind of line by line and go through it relatively slowly. It's relatively simple, but it's also complex. So the human core body temperature is about 37 degrees Celsius. You probably know that it's about 98 degrees Fahrenheit or 98.6 degrees Fahrenheit. The skin's temperature, though, is cooler. It's about 35 degrees Celsius. So we actually, our skin is cooler than our core body temperature. We cool ourselves by sweating, and we, depending on a person's physiology and depending on specific people, that could be once the temperature gets into the 20s or the 30s. Some people will sweat at lower temperatures than others. Some people are just sweatier people. And sweating cools the body by evaporating it. It takes lots of energy to evaporate water, and as that water evaporates, it takes that energy with it. So it'll take energy from your skin off into the air. And then that's going to cool your core because your core is going to lose energy to your skin, and then the skin is going to lose energy out into the atmosphere when your sweat evaporates. But sweating can't cool the body if the air is the exact same temperature as the skin, between 32 and 35 degrees Celsius. Really, that upper range based off of this, but 32 to 35 degrees Celsius, and anywhere from 50 to 100% humidity. We can't sweat like we can sweat. We'll sweat all day, but that sweat won't evaporate if the atmosphere is already saturated with water. If it already contains 100% humidity or even 50% humidity, it's not going to that sweat is not going to evaporate off of the person. So it's just going to build up, and it's not going to do its job, and it's not going to cool the person. So at that point, the body can't cool itself. If it's the same temperature and 50 to 100% humidity, then the heat is going to build up in the core, and the person is going to go into heat stroke and die regardless of physical fitness. And what this is essentially measuring is the wet bulb temperature. Now, you guys are all familiar with a temperature. The temperature outside might be 100 degrees Fahrenheit, but the humidity is only 50%. And we usually talk about temperature just in degrees Fahrenheit or degrees Celsius, either one. This diagram shows degrees Fahrenheit. So you just stick a thermometer out in the air and you're like, oh, it's 110 degrees Fahrenheit, which is a hot day. Like, I'm not going to disagree with that. It's a very hot day. What the wet bulb temperature is you basically take a thermometer and you wrap it in a wet cloth, and then you swing that thermometer with the wet cloth around and try to cause some of that water to evaporate off or to be removed from that cloth and cool that bulb of the thermometer. And the resulting thermometer temperature is the wet bulb temperature. So if it's 50% humidity and 10 degrees Fahrenheit, the wet bulb temperature is actually 92 degrees Fahrenheit. It feels like it's 92 degrees Fahrenheit. But if it's bone dry, if it's like 10% humidity, and if it's warmer out even, that wet bulb temperature is 78 degrees Fahrenheit. Okay, so it feels cooler than it is. That's why if you're in Phoenix, Arizona, and it's a blistering hot day of like 115, but the humidity is down to like 5 or 10%, then you can sweat and you can cool yourself and you'll be fine. Contrast that with being in Florida on a 115-degree day with 75% humidity. You're going to have trouble cooling yourself. So the limit of human adaptability is a wet bulb temperature of 35 degrees Celsius. So that's the same temperature as your skin, which are modeled to become increasingly regular in the tropics. So we're talking about this region of the planet, the tropics, between 1.5 and 2 degrees Celsius of warming. Remember that we breached 1.5 degrees Celsius of warming briefly this year in 2020, this previous year of 2024. Okay, and we're well on track of being past 2 degrees Celsius of warming by 2100. So if we have consistent or even just heat waves where the wet bulb temperature is above 35 degrees Celsius in the tropics, that's going to trigger the migration of billions of people out of the tropics into the higher latitudes, both north and south, but primarily north, because that's where A, there is more land mass to support more people, and B, there is more wealth and where they see more opportunity for themselves and for their children. So people are going to be migrating out of the tropics into the global north when this becomes more frequent. And before 2016, the wet bulb temperature, sorry, this is a little bit convoluted. There were wet bulb temperatures that were never measured or reported above 31 degrees Celsius before 2016. But a wet bulb temperature of 35 degrees Celsius um, was recorded in 2003, but it wasn't published until after 2016 in the Arabian Peninsula. Okay, so uh, in the Arabian Peninsula, we're actually seeing, and Pakistan, we're actually seeing wet bulb temperatures increasingly above 35 or 35 degrees Celsius or above. And those are in very isolated pockets. It's due to all the humidity from the Indian Ocean and the Red Sea and the Persian Gulf, as well as the intense heat of the Arabian deserts or Arabian Desert. Okay, so this map on the top right is showing 2060s, where we may have wet bulb temperatures that are well into um, you know, 35 degrees Celsius more frequently, 100 days out of the year in extreme cases. And that is not going to allow people to even survive in those areas. Okay, so they're going to have to migrate out of those areas. So something cheerful to end the PowerPoint on, the limits of human survivability. So there's a few more videos that you can check out. This first one is pretty good if you want a recap of climate change. So just the science behind climate change at a more basic level than what we discussed. The cryosphere is all the ice on the planet. So if you want to take a short tour of the cryosphere with NASA, go for it. We may show one or both of these in class. And if you're really into how are climate models created? How are climate models made? I've talked about climate models in terms of a climate model will project this or project that. Check out this video. It's a little bit more technical, but it's about climate models, and this is a really cool area of research and someplace that you could find yourself in if you're interested in this type of thing as a field. Okay, I'll keep this relatively brief because this PowerPoint's already pretty long. But the greenhouse effect, local and regional human activities can have impacts at global levels. That is absolutely true with the greenhouse effect. We know what the greenhouse gases are: carbon dioxide, methane, water vapor, nitrous oxide, and chlorofluorocarbons and hydrofluorocarbons, HFCs. While water vapor is a greenhouse gas, it doesn't contribute significantly to global climate change because it has a short residence time in the atmosphere. It just precipitates out. It rains, it snows. But the more water vapor that you have in the atmosphere, the stronger those storms are going to be, as well as the more heat that you have in the atmosphere. The greenhouse effect results in the surface temperature necessary for life on Earth to exist. That is absolutely true. Life cannot exist on the surface of the Earth if it wasn't for the greenhouse effect. It would be about 30 degrees Celsius colder than it is right now if it wasn't for the greenhouse effect, and the planet would be a frozen ice cube. But too much of a good thing can be bad, which is why we talk about the negative effects of the greenhouse effect more often. Carbon dioxide has a global warming potential of 1, and is used as a reference point for all of the other greenhouse gases. And then for increasing greenhouse gases, identify the threat to human health and the environment posed by an increase in greenhouse gases. Global climate change caused by excess greenhouse gases in the atmosphere can lead to a variety of environmental problems, including rising sea levels resulting from melting ice sheets and ocean water expansion. So this is warm ocean water expansion. As the ocean heats up, that water expands. And disease factors spreading from the tropics towards the poles. We really hit that with the infectious disease PowerPoint a few weeks ago. This problem can lead to changes in population dynamics and population movements and response. Okay, so they're talking about climate refugees and people that have to migrate out of their ancestral homelands due to the climate no longer being facilitating human life, whether that's agricultural, whether that is heat stress, whatever. And then we got the long global climate change learning objective, explain how changes in the climate, both short and long term, impact ecosystems. Earth has undergone climate changes through geologic history. We've talked about that ad nauseum throughout the year. And there's been major shifts in global temperatures caused by periods of warming and cooling as recorded with CO2 data and ice cores. Okay, so CO2 and temperature are highly correlated, so much so that there is a very high confidence of cause and effect relationship. Um, Effects of climate change include rising temperatures, melting permafrost and sea ice, rising sea levels, and displacement of coastal populations. Marine ecosystems are affected by changes in sea level, some positively, such as in newly created habitats on now flooded continental shelves. So that could be seen as a positive for ecosystems, and some negatively, such as deeper communities that may no longer be in the photic zone of seawater. Winds generated by atmospheric circulation help transport heat throughout the Earth. Climate change may change circulation patterns as temperature changes may impact Hadley cells and the jet stream. Oceanic currents, or the oceanic conveyor belt, carry heat throughout the world. When these currents change, it can have a big impact on global climate, especially in coastal regions. Okay, again, there's a lot of unknowns there. Unequal warming and cooling, potentially cooling of the northern hemisphere, but that could be counteracted by the other things that are causing warming of the northern hemisphere, such as the ice albedo positive feedback loop. Again, lots of complexities with global systems. Um, in general, though, this will definitely warm the tropics. Climate change can affect soil through changes in temperature and rainfall, which can impact soil's viability and potentially increase erosion. Earth's polar regions are showing faster response times to global climate change because ice and snow in these regions reflect the most energy back into space, leading to a positive feedback loop, that ice albedo positive feedback loop. As Earth warms, this ice and snow melts, meaning less solar energy is radiated back into space and instead is absorbed by the Earth's surface. This in turn causes more warming of the polar regions. Global climate change response time in the Arctic is due to positive feedback loops, including melting sea ice and thawing tundra. The thawing tundra is the permafrost and the subsequent release of greenhouse gases like methane and carbon dioxide. One consequence of the loss of ice and snow in polar regions is the effect on species that depend on the ice for habitat and food. And then with ocean warming, the causes of ocean warming is caused by the increase in greenhouse gases in the atmosphere. Ocean warming can affect marine species in a variety of ways, including loss of habitat and metabolic and reproductive changes, pushing organisms outside of their tolerance zone, all of that stuff. And then ocean warming is causing coral bleaching. So remember that bleaching events, I'm going to keep repeating this, are occurred by warming oceans, by marine heat waves, not by ocean acidification, but by marine heat waves. Ocean acidification is another problem that the oceans are facing and that corals especially are facing, so we should know the causes and effects of that. Ocean acidification is the decrease in pH of the oceans, primarily due to increased CO2 concentration in the atmosphere, and can be expressed as chemical equations. As more CO2 is released into the atmosphere, the oceans, which absorb a large part of that CO2, become more acidic. Again, it's because of the formation of carbonic acid. Anthropogenic activities that contribute to ocean acidification are those that lead to increased CO2 concentrations in the atmosphere, burning fossil fuels, vehicle emissions, and deforestation. And those vehicle emissions are really fossil fuels as well, the gasoline, the diesel from vehicles. Ocean acidification damages coral because acidification makes it difficult for them to form their shells due to a loss of calcium carbonate. So remember that their shells, they have more difficulty forming their shells. They spend more energy maintaining those shells, and they may have their shells erode away or dissolve away at extreme levels of acidification.